today we are going to discuss about another technique for image enhancement, that is a homomorphic filtering, and that homomorphic filtering is performed in frequency domain. As we can see from the figure, that the left side of the figure is both degraded images while the right side of the figure is the improved one. So we perform a different kind of operations to improve the quality of the images. We have already discussed about the different methods for image enhancement, that some of them are in spatial domain and some of them are in frequency domain. In frequency domain image enhancement technique, we have already discussed about low pass filtering operations and high pass filtering operations. So now we are going to discuss about homomorphic filtering. So homomorphic filtering is a frequency domain procedure for improving the appearance of an image. So it can be represented by image can be modeled as illumination reflectance model, in which f of x comma y is equal to I of x comma y multiplied with r of x comma y. I of x comma y representing the illumination component and r of x comma y representing the reflectance component. So illumination component is a slow spatial variation or a low frequency component, while reflectance components tends to vary abruptly, particularly at the junction of dissimilar objects. So those are high frequency component. Now we want to manipulate either illumination component or reflectance component. So for that we need individual reflectance component, individual operations on a reflectance component or illumination component. So if we are going to take the Fourier transform of an input image f of x comma y, then it will become f of u comma v, which is not equal to the Fourier transform of individual component of I x comma y and the Fourier transform of r x comma y, because the Fourier transform of the product of two functions is not separable. So we choose another method in which we are going to take the log of input image. So z of x comma y is equal to ln f of x comma y, which can be further extended as ln I x comma y plus ln r x comma y. Now the Fourier transform of z of x comma y is equal to Fourier transform of ln f of x comma y, which is equivalent to ln Fourier transform of ln I x comma y plus Fourier transform of r x comma y. Now the Fourier transform of z of x comma y is equal to z of u comma v, which is equivalent to Fourier transform of ln I x comma y is equal to f of I u comma v, and the Fourier transform of ln r x comma y is equal to f of r u comma v. Now we want to apply some kind of filtering operation, and the transfer function of the filter is h of u comma v. So now we multiply z of u comma v into h of u comma v, which is equivalent to h of u comma v f of I u comma v plus h of u comma v into f of r u comma v. Now again converting those images, this image s of u comma v into the spatial domain, we have to take the inverse Fourier transform. So s of x comma y is equal to Fourier inverse s of u comma v, which is equivalent to f inverse h of u comma v into f of I u comma v plus Fourier inverse of h of u comma v into f of r u comma v. So this Fourier term h of u comma v into f of I u comma v, an inverse of that is equivalent to I dash x comma y. An inverse Fourier transform of h of u comma v and f of r u comma v is equal to r dash x comma y. Now finally, because z of x comma y was formed by taking the natural logarithmic of the input image, so we reverse the process by taking the exponential of the filtered result to form the output image. Therefore, the enhanced image g of x comma y is equal to exponential of s x comma y, which is equivalent to e to the power I dash x comma y into e to the power r dash x comma y, where I, and which is equivalent to I naught x comma y into r naught x comma y, where I naught x comma y is exponential I dash x comma y and r naught x comma y is exponential r dash x comma y. The whole process of homomorphic filtering can be summarized into this below block diagram. So initially we have to take the log of input image, then we are going to take the Fourier transform, and then the Fourier transformed image is multiplied with the transfer function of the filtered, and then we have to take the inverse Fourier transform, and then finally we are going to take the exponential of the inverse Fourier transformed image. So the output image g of x comma y is obtained. So homomorphic filtering is a good deal of control can be gained over the illumination and reflectance component with a homomorphic filter. So it treats the low and high frequency component in different ways. This figure shows the radial cross section of homomorphic filter transfer function, where gamma h and gamma l are the upper and lower limit. So if gamma of L is chosen to be less than 1 and gamma of H is greater than 1, the filter function tends to decrease the low frequency and amplify the high frequencies. The shape of the function given in the previous figure can be approximated using a high-pass filter transfer function. For example, using a slightly modified form of the Gaussian high-pass filter function yields the homomorphic function. So h of u comma v is equal to gamma of h minus gamma of l in bracket 1 minus exponential of minus c d squared by d naught squared bracket close plus gamma of l, that will that is the DC component that will shift it in the upward direction. Now in the Gaussian high-pass filter-based homomorphic filter does not have any kind of ringing effect, but there is a poor transition between gamma L and gamma H. So we can also use Butterworth high-pass filter function with the added advantage of more control over the sharpness of the transition between gamma L and gamma H. But the disadvantage is that as we goes on increasing the order of the filter, then there will be a secondary lobes that will create a ringing effect. But the major advantage is that we have a sharp transition between gamma L and gamma H. Now in the example, we can see on the left side of the figure that there are no finer details available in this figure. So now we are passing this figure to a homomorphic filter where we have chosen gamma L is equal to 0.5 and gamma H is 2.0. So when we are choosing gamma L less than 1 and gamma H greater than 1, then we are going to attenuate the lower frequency component and amplify the higher frequency component. So after passing through a high pass filter, a homomorphic filter which is a high pass filter, we can find a more finer detail in this figure. So a reduction of dynamic range in the brightness together with an increase in the contrast brought out the details of the object inside the room and balanced the gray levels of the outside wall. Now another example is this PET image in which there is a tumor in the brain and lungs. So if it passes through a homomorphic filter, then you can clearly see this tumor in the brain and lungs. So some review questions are: what is homomorphic filtering and where it is used? What is the illumination and reflection components?